So you're welcome back, and we'll just continue from where we stopped. But this time we'll be looking through information theory in terms of information measures. Okay. See. Now, you recall in our last lecture that we were able to describe two fundamental limits, okay? The first of which was the data compression limit. And the other extreme was the data transmission limit. So we were able to also tell that the data compression limit actually gives us an average value in terms of the number of bits that can be used to describe the random variable, and we call that the entropy. And we said this was the minimum value of the mutual information between X and Y, given that X was transmitted and Y was received, okay? And that the transmission limit, excuse me, and that the data transmission limit actually describes the capacity of the channel. See. And here, we also said that this capacity mathematically is described as the maximum value of the mutual information. So this, in every way, now gives us enough reason or information to design the system in terms of what can be transmitted and what is expected to be received. And then looking up what Shannon described in his classical paper, there he was able to put forward that for us to have reasonable transmission, an error-free or near error-free transmission, then this data compression limit has to be less than the capacity of the channel. So technically, the fundamental problem of communication based on what Claude Elwood Shannon said is therefore the problem of reproducing at one end exactly or approximately what was transmitted at some other point. So we want to reproduce at point Y what was sent at point X, such that X should be either the same, Y should be either the same as X, or better still, an approximate value. So hence, it is probable that the selected message may either be distorted or undistorted. So since what we get to receive may either be distorted or undistorted, the information contained in the message, therefore, is defined as uncertainty, or better still, quantifiable uncertainty. Quantifiable uncertainty. And this quantified uncertainty is therefore modeled as a random variable. So if we are therefore concerned about the message contained in the information, okay? Or better still, the information contained in the message, let's put it that way. If we are worried or bothered about that we have a message, what is the information contained in that message? What therefore is information? Because we already know that we want to transmit at this point and receive something equivalent at this point. So it means that this message symbol contains the information that is required at this point. And we've been able to tell that we are not so sure what we'll receive here, because the message that contains this information we are going to receive here may either be distorted or undistorted, and as such, we can actually denote this as some quantified uncertainty, which is now described mathematically as a random variable. And so, what therefore is the information? I know in our last class, we were able to describe that information is a measure of the uncertainty associated with the transmitted message signal. So this therefore implies that for a system which transmits, say, messages M1 to MK, so let's say M1, M2, all the way to MK, with the probabilities of P1, P2, all the way to PK, the amount of information transmitted through the message MK with the probability PK will therefore be given as I sub k being the same as log 1 over P sub k base A. Now, if here we have the channel for which we are transmitting, so X is transmitted, Y is received, and we know at this point, MK is transmitted with probability PK. So let's put that in the system. So message MK goes in, but based on what's happening in this system, we try to use a practical system to analyze that in our last class. So that induces some level of uncertainty into this. And now we are not so sure what information will be in the received message. But we are certain that if we are able to design some interesting codes, we should be able to receive the information contained in the message with minimal error. Okay, that's the essence of error control coding. So the idea now is this. Should this probability distribution increase or extend to 1 such that it is certain. As the probability, if is highly certain. What will happen? So what about if it is impossible? What will also happen? That means the probability is 0. Okay? And then what will happen between 0 and 1? So it means that we have P sub k taking on values between 0 and 1. So at this point, we know it is certain. At this point, we know it is impossible. Now, if we plug in these parameters, you see that the information gained, considering base 2, because that's what we are really playing with binary, we already mentioned, because we are playing with binary, the unit of measure will be bits. If we're playing with base 10, it will be Hartley or Band. If we're playing with base E, that will be natural logarithm, that will be NAT, but we are playing with base 2. So this is going to be log base 1 over 1, which will be equal to 0. So no information. That's the idea when it is certain, okay? So based on the definition of information, when there is no uncertainty, okay, that is, the probability is the same as 0, this is impossible. And then when the probability is equal to 1, it means no uncertainty. We see that no information is gained. So there's no information gained when we are absolutely certain about the outcome of the event. So if the receiver knows the message being transmitted, the amount of information carried is 0. That's the implication, okay? Now, same with this. 1 over 0 is some infinite value, so that's impossible. Now, what if the probability distribution is far, far less than 1? Then you'll observe that the information gain will gradually move beyond 0. So the information gain will also be far, far greater than 0. So there is never loss of information if the level of uncertainty of the outcome is high. So the higher the uncertainty, then the more the information gained in the process. And then, should we have, for instance, the following probability distributions, P sub k and P sub j, then the composite information, IKJ, is the same as the sum of the individual mutual information. And this is very easy to prove. So let us assume this is K, J is the same as log to base 2, 1 over P sub K, P sub J. And we know from the laws of logarithm, so this is the same as log to base 2, 1 over P sub K, 1 over P sub J. And now this is the same as log to base 2, 1 over P sub K, plus log to base 2, 1 over P sub J. And you can see this is I sub K plus I sub J, which is the composite mutual information. So meaning if we have a system and we feed them with x1, s2, for which this has a probability P sub k, and this has a probability P sub j, then the information here, again, will be the composite information. And also, another property, which we also have described in the videos online in our previous lecture notes is that if, for instance, we have m being the same as 2 to the power of n equally likely messages, now the amount of information carried will be the same as n bits. So how is that? So n messages are equally likely and independent if the probability of occurrence for all of the distribution is the same as 1 over m. And therefore, here, we already know that the information is the same as log to base 2 1 over p sub k, for instance. And then if this is the probability of occurrence, since they are equally likely, it means that all the elements in the distribution have the same probability of occurrence, okay? So that's why they are equally likely. So if they are all 1 over 2, then it's 1 over 2, okay? So let's assume we have 0, 1 elements in this distribution. If they are equally likely, then it means both of them have the probability of 1 over 2, 1 over 2. Because by the law of total probability, the sum of the probabilities of all of these elements should be equal to 1, okay? Now, if that is clear, then it means that we have log to base 2, 1 over m, which is the same as log to base 2 m. 1 over m is the same as n. And we already know that this element has 2 to the n. Okay, so if we replace that 2 to the n base 2, so that's n log 2 base 2. 2 base 2, this will reduce to 1, so that's n into bracket 1, which is n bits. Okay. So I think that's enough of for information. Okay, so now that we have been able to clarify that information in generality is a measure of uncertainty associated with a random variable, with a transmitted symbol or signal, which we describe as a random variable, then what is the entropy? The entropy. Okay. So now, recall that in a communication system, as we already described, for us to get something like this, we're already saying that if this is a channel with capacity C, then we're already saying that the compression rate, H, should be less than this capacity. Else, there will be distortion, okay? Extreme distortion. So, in other words, H should be less than C. That's where we are going. Now, we've been able to tell that given X symbol containing M messages that contains I information transmitted over this channel, what is the possibility or likelihood that what Shannon said will hold? Okay? The problem of error-free reception. That's what Shannon talked about. Okay? Now, this entropy, therefore, H, is seen as the average information. So in other words, I want to transmit M1, M2, M3, M4 to Mn. Now, if I want to transmit all of these, there's every possibility I will overflow the channel. So can I take the average of these that will represent the information contained in all of these? That is compression. So if I'm able to do that, and I'll call that Mk. So transmitting Mk means that I'm transmitting the information contained in this. And this Mk should be less than the capacity of this channel. That's what we are trying to say. So if this is the information, entropy, therefore, is average information. I don't know if that is clear. Hello? I would love to get your feedback now. You've been doing too much talking. Are you still with me in this
Yes,
one?
sir, you can continue.
Okay. So it means that your entropy is directly related to your information. Let's put it that way. So if your information is the measure of uncertainty in the random variable, now entropy is the average information. So this means that the entropy is the same as the total information divided by the number of messages. That's the only way we can average over this. And statistically, the average value is the same as the expected value. Okay? So if that is what it is, then it means that we can actually describe the entropy statistically as the expected value of the information. Okay? And if we do this, then it means that we have sigma P, Pk, Ik. For k, taking on values from 1 to n, if this is Hk. Okay? And then we already know that I sub k is the same as log 1 over Pk. So it means that the entropy, which is the expected value, the average value of information for which I sub p is the same as the average value of the total probability. Now, times this, times your measure of uncertainty, then we now have that the entropy is the same as P sub k taking on values from 1 to m log 1 over P sub k. Now, this also can be designated as negative summation k equal to 1 to m P sub k log P sub k, where this negative 1 is the same as this inverse. That's your laws of logarithm, right? Now, if this is clear, then we can equally look up some of the properties of mutual information. So if the event is sure or impossible, that is, P sub k, it is sure, or P sub k is impossible, then the entropy is the same as 0, because log 1 over 1 is the same as, summation. This is summation. So that will give us summation 1 times 0 is equal to 0. And this is impossible, so that is 0. And if the symbols are equally likely and independent, that is P is the same as 1 over m, all the elements in the distribution have the same probability for all m, then the entropy will be the same as log m base 2. And this is not difficult to prove because here we have that the entropy is the same, equal to 1 to m, P sub k log 1 over P sub k. And now we have for all m, P1 log 1 over P1 plus P2 log 1 over P2 plus all the way to Pm log 1 over Pm. That's what we have, right? And we know that they all have the same probability. So it means that 1 over m log 1 over 1 over m plus 1 over m log 1 over 1 over m plus all the way to 1 over m log 1 over 1 over m. So this will now give us 1 over m log m plus 1 over m log m plus all the way to 1 over m log m. So in this case, we have 1, 2, 3, 4, 5 to m, to the mth order of this element. So we have m elements here. So we can reduce this to m, 1 over m log m, right? So this is what we have here. By the time we put all of them together, so that's what we have. By the time we add all of them to the mth entropy. So this will now give us m over m log 1 over m. Log m rather, sorry, not 1 over m anymore. So log m. So which gives us this. So when the probabilities of the message symbols are equally probable, then the entropy is the same as log m base 2, which is equal to log m base 2. And these are just simple, very simple stuff anyway. So also, we have that the upper bound on the entropy is the same as h max less or equal to log m base 2. Okay. Now, we can prove this quickly, though we have it in your notes, your online notes. But if we, let's say, okay, let's break this because it's kind of lengthy. Now, if we recall the property of natural logarithm, that's log to base e of x is less or equal to x minus 1 for all x greater or equal to 0. They are non-negative values, okay? When x is non-negative. So if we consider any two probability distribution, say PQ, in this case, on the alphabet X, okay? Now, we can say that the sum, k equal to 1 to m, piece of k log qk over pk base 2 exists. Now, if we say that this exists, for instance, then in terms of, because this is in base 2, and now we want to move from base 2 to base e, okay, to the natural logarithm. Now, for us to do that, we first want to convert to base 10, okay? And for us to do that, so it means that sigma k equal to 1 to m piece of k log qk over pk base 2 is the same as summation k equal to 1 to m piece of k. Now, we want to take log q k over pk base 10 divided by log 2 base 10. So we are converting this base 2 to base 10. Okay. Now, if this is clear, then for us to be able to convert to base e, we want to multiply this entire process, the right-hand side, by log e to base 10 divided by log e to base 10. So I'm just scaling. I will multiply by this parameter, and you agree with me. Let me write it nicely. Okay. Let's write this a little nicely. Here's base 10. So now I want to multiply this whole process. I want to scale it by log E base 10 divided by log E base 10. So doing this, I have not altered anything. So what I have here is still the same. So it means that this is just what I want to do. I want to multiply by this process. So this divided by this is still 1. So if we do that, then it means this whole expression here is the same as sigma piece of k to m, right? Now, this will be log qk over pk divided by log e to base 10. This is base 10 also, dot log e to base 10 divided by log 2 base 10. Now, if this log cancels this, so we'll come back to this expression, which is this divided by this. Do you agree with that, please? Hello? Do you agree with this expression?
It's getting complicated.
Sir?
So it's getting complicated.
Okay. Now, let's wipe this. Let's wipe this. Okay. Now, did you get it to this point? Hello?
Everything that is on the screen, there, I'm not getting it again.
Okay, everything here is not clear.
Yes.
Okay, so you are going to spare me 1 minute now.
But I understand the theory behind it. It's just the mathematics now.
Okay, now, so as it stands, is it that everything on the board now is not clear, right?
It's the current board now.
It's not clear, right?
Yes.
Okay, so let's.
But I understand the two lines, the first two lines.
This and this.
Yeah.
Okay, so let us wipe. Let us take it from the beginning. Okay. Now, this is okay. Okay, let's wipe this. Okay. Okay. Just trying to figure out. Okay. Now let's assume I have two distributions. Okay, described by their entropies. Say piece of k log 1 over piece of k minus summation piece of k log 1 over piece of k. Okay. So here we can say piece of k log 1 over piece of k minus log 1 over piece of k. which will be minus log piece of k plus log piece of k, which will now be log piece of k divided by piece of k log piece of k. Do you understand this simple analysis?
Yes.
Okay. Now, since we have this distribution, for instance, this is by total probability, this is right. So should we describe these two distributions as Q sub k and P sub k? Because by total probability, the probability, sum of probability of k is the same as the sum of probability of q is the same as 1, right? The sum of all probabilities in the same distribution must be equal to 1. It cannot be more than 1. It can't be greater than 1, isn't it?
Okay, yes, of course.
That's the law of total probability.
Between zeros and 1.
Yeah, it is between 0 to 1. So it cannot be, it's more like saying the efficiency of the machine cannot be more than 100%, right?
100%.
Isn't it? Yeah.
Yes.
So if, for instance,
Yes.
we have two distributions, okay? And now the entropy of those, the difference between, we are still going to talk about relative entropy. I don't want to just jump the gun. Now, by the time we are checking the distance between these two distributions, it's more like taking the relative distance between them, okay? And now, considering these two distributions, we can relate their entropies by this expression, going by what we have here, right?
All right.
Isn't it? Now, if that is clear, I don't need this, okay? I just jumped the gun, and I want to jump the gun again, all right? So I want to clear this up.
All right.
And say, well, going by that, we can simply put up what we wrote earlier to be summation k equal to 1 to this piece of k log q sub k over p sub k. You know how we got here now?
Yes.
Okay. Now, this is base 2, right? And now, recall the property. This is the property of natural logarithm, right? We have so many theorems, so many rules, so many properties, that the natural logarithm of x is less than or equal to x minus 1. So there's an inequality rule with respect to the natural logarithm of some random variable x. When x is a non-negative value, that is x is greater than or equal to 0, okay? Now, for me to be able to do this, what is my goal? We want to actually investigate the upper bound on entropy, that H max is less than or equal to log m base 2. This is what we want to prove. Upper bound on entropy. Is the same as this. Okay?
All right.
Now, if this is true, recall your regular mathematics. Now, I want to solve something in my base 2. Now, I want to convert. I want to use my regular calculator. Then I have to convert to base 10 if I'll be able to solve that, right? And then convert back to base 2. So for us to convert this to base 10, recall that log A base K, if we want to convert this to base 10, then we have to take log A base 10 divided by log K base 10. This is base conversion to base 10 in logarithm. You recall that?
Yes.
Okay. Now, if you recall this, then this particular expression here, we want to convert it from base 2 to base 10. We know the sum of these probabilities is equal to 1. This is equal to 1 by law of total probability, right? But this particular expression, we want to convert from base 2 to base 10, so we are able to work towards the natural logarithm because we need this inequality sign here to be able to justify this process, to be able to figure out or better still derive the upper bound on the entropy. Okay? So that's where we are trying to work towards, just little manipulations here and there. So if that is clear, then it means that I have to now convert this to base 10. So what I have here is still, we'll repeat that, the sigma, taking values from k equal to 1 to m, p sub k, times, then this now, log qk, log q sub k divided by p sub k base 10 divided by log 2 base 10. This is what we mean here, to convert to base 10. So we now have to take log q sub k divided by p sub k base 10, right? Divided by 2, log 2 base 10. So this expression and this expression still mean the same thing. We've not written anything, that is different. Okay?
All right, sir.
Is that clear?
Yes, continue, sir.
And now I want to do a little scaling here. Now that we have done this, I want to do a little scaling. But before I do the scaling, let us expand this. So let's say this is the same now as sigma taking on value from k to m, p sub k, times, let's say this is 1 over log 2 base 10 times log qk over pk base 10 divided by 1. I've written the same thing. So if I multiply 1 by this, I come back to this. If I multiply this by 1, I come back to this, right?
Okay.
I've written the same thing in just in a different way, just separating the parameters, right? Is this clear?
Yes, no difference.
Yeah. No difference.
Yes,
Now,
continue.
if I should turn this 1 to k and turn this 1 to k, there's still no difference because k will cancel k. You still be 1.
Yes.
Now, that's exactly what we did. Then I'm not saying that, well, rather than do this, I want to be able to convert to another base. Okay? So rather than do that, this numerator and denominator, I want to place my log e base 2, right? That's what we mentioned earlier, isn't it? E base 2.
Yes.
And put my log e base 2 here. No, it should be base 10, sorry. Because the other base is 10. So we need something uniform, right? E base 10, log e base 10. Now, if this log e base 10 cancels out log e base 10, because this is also base 10, this is base 10. But if this cancels out, we still have what we have here. We have not written anything different yet.
Yes.
Isn't it?
It's still the same.
Exactly, it's still the same. But now, if we now come back to this expression, now let us look at the base conversion and compare it with these two parameters. You see that when we have the common base here, 10, 10 here, AK here. So it means that when we have this expression, we can take this value, log of this value. Let me turn it to the normal color, please, so that we don't mix things up. we can take log, this is A, this is A, this is K, this is K, right? So it means in this case, we have log E base 2, log QK over PK base E. Compare this with this. So it means that log A base 10 over log K base 10, if we compress it again, going backward now, you know, we did it this way before. So we want to take it backward now. So it means that once we have our log here, this A comes here, this K comes to the base. So this is going to come up, and then this is going to be the base. And this is now going to be the log value, and this is going to be the base relative to the conversion process. Is that clear?
Yes.
Yes. Is it clear before I move on?
Yes, it is.
So then it means that we can now move on to say sigma K equal to 1 M P sub K log E base 2 dot log QK over PK, that's base E. Isn't it? Is this clear?
Okay.
Now you will observe that this parameter log QK over PK base E is equivalent to this property of natural logarithm. And if we replace it here, this equality will turn to this inequality, x minus 1. Where x, now let me bring it out. Now, the law of natural logarithm says log x base E is less than or equal to x minus 1. So in this case here, x is the same as qk over pk, right? So that we can now replace log qk over pk base E to be less than or equal to qk over pk minus 1. So we can replace this entire process here with this, going by the law of natural logarithm, which is here. Is that clear? Is that clear?
Yes, sir. Let's continue.
Have you been able to process that? So we move on.
Yes, we can move on.
Okay, so it means that here we now have that sigma k equal to 1 to m p sub k log to base 2 qk over pk is less than or equal to, now we can bring this out, right? It's more like a constant. Log e base 2 then we bring this out, log e base 2, then this sigma k equal to 1 to m p sub k. You know, we already introduced the inequality into bracket qk over pk minus 1. Is it clear? Is it clear? So at least you got it to this point, and now we have substituted this. We just rearranged, we brought this out, and then we have sigma pk, which is this, and this log p sub q sub k over p sub k base e is now replaced by qk over pk minus 1. And then the inequality sign comes in because we just evoked the property of natural logarithm. So this is our new expression. Is that clear?
Yes, let's continue.
Okay, so let's wipe this now. Okay, so now it means that sigma k equal to 1 to m piece of k log this 2 cubes of k over piece of k is less than or equal to. Now, if q pk we cross, if we multiply through, so we are going to have qk minus pk, because pk would cancel out pk here, so we have qk minus pk times 1. That would be qk pk. Is that clear?
Exactly.
Yeah, so we now have less or equal to log e base 2 sigma k equal to 1 to m. We now have qk minus pk. Yeah. So
Yeah, super.
So now this now is the same as this, less or equal to log to base e, then sigma k equal to 1 to m qk minus sigma pk k equal to 1 to m. When we open up this bracket, right?
Yeah.
But we already know by the law of total probability, this sigma qk is the same as sigma pk is the same as 1. The sum of the probabilities, which is the total probability of a distribution, cannot be greater than 1. It's the same as 1. And it cannot be less than 1, right? So if that is true, so it means that 1 minus 1 will give us 0 here. So this entire process will reduce to 0. Isn't it? And 0 times this will be 0. So now we are going to be having sigma piece of k log qk over piece of k base 2, k equal to 1 to m is less than or equal to 0. Is that clear?
Yes, sir.
Okay. Now, if this is clear, then we now want to open this up. Okay, we now want to open this up. So this now is the same as sigma k equal to 1 to m piece of k log qk minus sigma k equal to 1 to m piece of k log 1 over pk is less than or equal to 0. We just open this up and it's the same as this, right?
Yes, it's clear.
Okay. Now, if this is clear, no, this should be plus. It's plus. Now, this is, if it's minus, then this is not here. So let's designate it properly. This is minus pk. This is division, right? By law of logarithm is log qk minus log pk. Isn't it? Isn't it?
It's okay, sir.
No, is it clear? We are doing the correct thing now, right?
It is. It is.
Now, so it means that if we move this to the other side, so we have negative sigma piece of k log piece of k, this is k equal to 1 to m, is less than or equal to negative sigma k equal to 1 to m piece of k log q sub k.
Are both ends supposed to be negative?
This is negative here. This is
yes, when you cross that one over.
When this crosses the equality sign or inequality sign is negative, it becomes negative, isn't it?
Okay. It's true.
Yeah, because this is positive. This is QK minus
it's okay.
QK, right? Yeah, so it's not negative,
All right, so it's
negative.
clear.
It's clear. Now, you will recall that by law of logarithm, log 1 over p sub k is the same as negative log pk. Right? You recall this?
Yes.
Now, if you recall this, so it means that sigma k equal to 1 to m p sub k log 1 over p sub k is less than or equal to sigma p sub k log 1 over q sub k for k equal to 1 over m. Right? So these are the entropies. These are the entropies. And remember, we are trying to figure out the upper bound on the entropy, right? The upper bound on entropy. Now, if, for instance, the distribution, the probability distribution is equally likely, or they are equally likely and independent, so it means that the probability distribution Q sub k will be the same as 1 over m. If they are equally likely, they all have the same probability. The M message symbols. Right? If we have two symbols, X and Y, if they are equally likely, it means that we have two symbols, so the total probability is 1 divided by 2. So it means that X have probability, X is half, then probability Y is also half. Right? Now, if there are four symbols, A, B, C, D, so if they are equally likely, that will be 1 divided by 4, right? So it means that the probability of A is equal to probability of B is equal to probability of C equal to probability of D is equal to 1 over 4. So if there are M symbols, the probability, if they are equally likely, so the probability will be equal to 1 over M. Right?
Yes.
So if they are equally likely, then it means that Q sub K, the probability of Q sub K will be equal to 1 over M.
Okay.
Right? Okay.
So
now, if that is clear, then we can now put this up here to say sigma k equal to 1 to m p sub k log 1 over p sub k less than or equal to sigma k equal to 1 to m p sub k log 1 over 1 over m. So this will be less than or equal to will now be the same as sigma p sub k, k equal to 1 to m log m, right? So we can rewrite this to say this is the same as log that's base 2, m base 2 sigma p sub k, k equal to 1 to m. And we already know that the sum of total probability is 1, so this will be log m base 2 times 1, which will be less than or equal to log m base 2, which is sigma p sub k. If we bring this down, log 1 over p sub k base 2, k equal to 1 to m. Right? So where this is the maximum entropy, which is less than log m base 2, as you will say, Q is the end of proof, which gives us what we're asked to prove, this and this. Okay. Is that clear, please?
It's clear, sir.
Okay. Now, what I just want you to understand is they are pretty simple and straightforward. It's just that at some point you want to evoke some theorems, you want to evoke some proof, just to justify what you're trying to say, okay? Now, just in passing, we already established that the entropy is the same as the expected value of the information, which is 1 over P of X, right? So we can actually designate it this way, and you will observe that the entropy does not depend on the actual values of the random variable or taken from the random variable. They're only dependent on the probabilities, okay? Piece of X or piece of Y or piece of whatsoever, okay? So we play with the probabilities, okay? And since we already know that given that X is transmitted and Y is received, then it means we can have the entropies relative to the source and the destination symbols, okay? So in other words, the source entropy or the input entropy will therefore be designated as H of X, which is the same thing as sigma P of X log to base 2, 1 over P of X. Why the output entropy will be designated as sigma P of Y log 1 over P of Y, base 2. So should we ignore the base, just know that we are playing with base 2, okay? And this is also the same as negative P of X log P of X. And this is also the same as negative sigma P of Y log P of Y. Okay? So where this is the destination or output entropy, and this is the source or input entropy. Is that clear, please?
Yes, sir.
Okay. So now if we have the source and the input entropy, then it will become necessary to define the entropy of the source relative to the destination and the entropy of the destination relative to the source. So that means when we have X, when we send X and we get Y, so it means that here we actually have on this chain the probability of receiving Y when X was transmitted. We call this, if this is the probability of X and this is the probability of Y, then along this channel, you see that this channel is therefore described by the probability distribution of receiving Y given that X was transmitted. Is that clear? When we get to channel matrix, okay, we make this clearer, okay? So it means that there is the possibility that we are going to receive X when Y is transmitted. So we call this conditional probability. Okay? Now, if this is conditional probability, the entropy that is related to the conditional probability will also be what? Conditional entropy, which will now be either H of Y given X or H of X given Y. Do you understand now? Because that we have H of X,
yes,
we have H of Y. So if we look at it the other way around, you know, this is the ideal way. This is the ideal thing, okay? Let's wipe the board. Now, the ID process is that we have transmitted X and we are going to get Y. Okay? So should I consider the entropy of Y given that X was transmitted is fine? But what if I now look at things the other way around? You know, that is more like the wrong way of describing the system, right? So I have transmitted X. I'm expected to get Y. But now I'm looking at, rather than look at things from this dimension, I want to look at things from this dimension. Okay? It's more like the wrong way of looking at the system, right?
Yeah.
Yeah, it's the wrong way. So we'll call it equivocation. It's like something done to deceive, right? Okay, it's not when you're looking at fallacies and all of that in your mathematical logic. So we'll call this equivocation because now we want to view the entropy of X given that Y was received. So this is what we call equivocation of X with respect to Y. Okay? Does that make sense?
Yes, sir.
Okay. So mathematically, we now have to begin to represent this statistically now. So we already know that the source entropy is given as the probability of X log 1 over P of X. Now, the output entropy is given as sigma P of Y log 1 over P of Y. Now, the equivocation of X with respect to Y, which is the entropy of the channel input X, given that Y, the output, was received, is given by sigma, say ij for X and Y, probability, or let's just designate it as S and Y. And let's designate it as S and Y. Sy give us probability of X, Y, log 1 over the probability of X given Y. Okay? And also, the output entropy, or better say the conditional entropy of Y, that's of the output given that X was transmitted, is not the same as sigma xy P of xy log 1 over the probability of receiving Y given that X was transmitted. Okay? Now, if we've been able to do this, recall that we have a system where X symbol was transmitted and Y was received. And should we try to designate this properly, then we should be looking at the joint probability distribution, okay, which describes the relationship between X and Y. And now, should we do that, then we should also have the entropy relative to this as the joint entropy, okay? So that the joint entropy, X and Y, describes the average uncertainty of the entire communication system, okay? So this now, which is the joint entropy, is the average uncertainty. Oh, no. Uncertainty of the entire communication system. Okay, so it means that this now is the same as sigma xy, the joint probability distribution, log 1 over the joint probability distribution. Okay? Now, you will observe that we have the source entropy, the output entropy, the conditional entropies, then the joint entropy. Now, by chain rule, the joint entropy, the conditional entropy, and the source and destination entropies are related. So let's just write this. And then we now see that by chain rule, we'll just prove one or two of them, or then we see how far we've been able to go today. Okay. Now, you see that by chain rule, the joint entropy is the same as the conditional entropy plus the output entropy, and it's also the same as the conditional entropy plus the source entropy. So when we are considering the equivocation, then we add that to the output entropy. Now, when we are also considering the conditional entropy of receiving Y, given that X was transmitted, then we add that to the source entropy. Okay? And this is what we call the chain rule, okay, which describes the relationship between these entropies. Now, let's just show one of them. Let's see how to work around one of them coming from the probability distribution functions. Okay. So let us show that H of, okay, let's show that H of the joint entropy is the same as the equivocation plus the output entropy. So we already know that the joint entropy is given by sigma sy. Now, in some tests, they use double sigma notations. Okay, let's try that out. They use double sigma notation. That is sigma s, sigma y. Okay, p, the joint probability distribution function, log to bestow 1 over p sub xy. Okay, so we can also put this the same way, or better, let's put it here. This is the same as sigma xy, p xy is negative log p xy. So we are doing the same thing. Now, if anything is confusing, please draw my attention. Now, I want you to recall the Bayes theorem. Bayes theorem. And it states that the joint probability is the same as the product of the conditional probability and the output probability here. That's the equivocation times this. And in this case, we have that p xy is the same as the conditional probability times p of y. Okay. Now, this is common, right? So if we replace this process here with this, then what do we get? So it means that the joint entropy is the same as negative sigma xy, P of xy, log P of x given y, P of y. Is that clear? And then we can also expand this. This is the product. So we are going to have a sum. Should we try to analyze this little mathematical problem? So h of xy would be the same as negative sigma P of xy. This is xy. That'll be log P x given y plus log P of y. We are still doing the same thing, right? Nothing has changed right now. Everything is still the same thing. And recall there's a negative parameter here because we equated into this expression. So now if we expand this, then we are going to have negative sigma P xy log P of x given y. No, that's negative sigma xy P of xy log P of y. Okay? Are we clear? Is this okay? And now we are going to do one more thing here. Now we're going to evoke the law of total probability. So by the law of total probability, we have that we're dealing with y, P of y is the same as the joint distribution, say sy, which is P of xy, which is the same as the sum of this product. Going by Bayes' theorem, this is the same as this. So P of y given x, P of x, this xy, right? So by Bayes' theorem, this expression is the same as this expression, and they are all equal to 1, right? Okay. So the sum of this is equal to the sum of this, what is equal to 1. So if that is true, then we can replace this expression with P of y, okay? So that the joint entropy will now be the same as negative sigma xy, P of xy, log P of x given y, minus sigma P of y, log P of y. And now if we move these negative values, so we are going to have sigma xy, P of xy, log 1 over P of x given y, minus plus sigma P of y, log 1 over P of y. And now this is the same as the h of x given y plus h of y, which is the chain rule. So here we say end of proof, right? Now, is this clear? Is this clear, please? And if you understand, you just realize that we are just playing with the same technique, okay? It's just a little manipulation. We'll call a few theorems, a few rules and all, and just walk around the entire process and boom, we are where we want to be. Any question, please? Is this clear, please?
I don't think the whole thing is interesting. I think if we had solved the examples, it will make it very clear.
Yeah, the examples can be more than this. These are the examples we are solving.
Okay.
Well, I think right now we'll try as much as we can not to go numeric anymore. When we get to coding, we'll begin to play with some integer values, zeros and ones, and polynomials. But right now we are just going to be playing with symbols. So we may not be solving some numeric examples where we'll play with zeros and ones and all of that, because you want to design systems, and you design systems based on algorithm. And there you want to assign parameters to some constants and variables when you are drafting your algorithm and programming. So you are not playing with numeric values, right? You may only test with some numeric values, yeah. So the bottom line here is to understand the discipline, because I want to transmit a particular information. And just like we are talking, we are transmitting, receiving, and transmitting here. So from my end, I have a transceiver. That's why I'm able to talk to you and also get a feedback from you. From your own end, you also have a transceiver. Okay, but now what we say, we cannot tie it to either a 0 or a 1, but we can actually tie it to some random variables. So say, well, this random variable describes what Dr. Ebaze is saying, right? And then it is encoded and boom, it goes all out. Now we're using the internet, then there's some packetization, and then it goes all the way, and then there's a reconstruction from your end, and you seem to hear me. Okay, I think when we had our first class today, before the break, some of us had network issues. At some point, I was logged out of the system. That was total loss of connection. So everything I must have said at that instant must have been lost in transit because there was loss of connection, right? So at that instance, we can actually talk of packet loss, right? But everything that must have happened, you now see that we just begin to deal with some defined parameters. And now that we are using the Wi-Fi based technology and all of that, we begin to talk about cryptography, right? Encryption, decryption, right? You want to use your DS, AES, and all of that, right? Isn't it? So to encrypt, decrypt with your symmetric key and all of those things. And it's coding. What is done there is coding. Okay, so now whether you want to take this program a notch higher and go into cryptography, perfect. This is the basis for it. Okay, now whether you want to go into signal processing, this is the basis for it. So long we now have to communicate in such a way that what we are transmitting have to be encoded. And in encoding it, we also don't want some eavesdroppers to just eavesdrop and capture what we are saying. You know, there's the need for confidentiality. So we are doing some encoding, decoding, and all of that. And we want to be sure you receive this accurately wherever you are and all of that. That's what it is. So if we are dealing with the information and coding concept in that dimension, so I think we have to go purely symbolic. So we'll be playing with symbols going forward. Is that okay?
All right, sir.
Okay, now. So if this is clear, then we'll just talk about relative entropy. Then I thought we'll be able to cover so much today, but I think once we are done with information measure, we'll take a break for the day, okay? And see what we'll be able to achieve some other time. You know, if we could extend the number of times we interact in the week, then that'll be fine. If we really want to run through the entire process as fast as we can. Okay, so relative entropy. So this is described or denoted the relative entropy between P and Q. Okay, so the relative entropy of two probability mass functions, say P of X and Q of X, is a measure of the distance between the two probabilities. So it means that the relative entropy between P and Q is the same as sigma P of X log P of X divided by Q of X. Recall what we did earlier in resolving the upper bound on the entropy. So we already know that this is the expected value. Is of P log P of X divided by Q of X. So this relative entropy is usually referred to as the callback Leibler distance or divergence. And here you observe that the relative entropy is a measure of the inefficiency of assuming that we'll receive the distribution Q when the original or right correct distribution is P. Okay? So the bottom line is I want to transmit X and receive Y such that X is, you know, the representation of X somehow. And here, X, the original distribution of S is P. But now, for me to be able to analyze this based on what may be going on in the channel, there's another distribution Q. Now, there's every possibility that I will receive Q when I'm supposed to receive P. So for me to be able to design the correct code, I need to know the relative entropy between P and Q, then add it to the entropy of P. So in other words, I'll have to, at this point, for effective recovery, design a code, H of P, because H of P describes the compressed data. And now, since there's another distribution Q that is posing a little confusion, and now my receiver, Y, may confuse the distribution Q, P for Q rather. So since that's what it is, so I want to, in the receiver, I want an algorithm to run with a code H of P plus the relative entropy between P and Q, okay? Because the relative entropy is the measure of the inefficiency of assuming that the distribution is Q when the true distribution is P. So if we know the true distribution P of a random variable, for instance, we should be able to construct a code of description, of average description H of P. And once we do that, if we now use the code distribution Q of X, for instance, we would need H of P plus the relative entropy bits on average to describe the random variable. I don't know if you understand what this is all about from what I just said.
It's clear, sir.
Okay. Now, if that is clear, we now see that some other properties of the relative entropy is such that it is always non-negative. Okay, it always assumes a positive value. It's always greater than 0. But it will be the same as 0. Sorry. To be the same as 0 if and only if the distribution P is the same as the distribution Q. Okay? So here, I will now say technically, the relative entropy is not a true distance between the distributions, since it is not symmetric and does not satisfy the triangle inequality, where we say A plus B is greater than or equal to C. It doesn't satisfy this, and it's not symmetric. So it's not a true representation of the distance, okay? But it's just a measure of that inefficiency. Okay. Now, if this is clear, then we can now talk about the important point we started our class with, which is mutual information. Described as I of xy. So here, this is the amount of information gained per received symbol, right? The amount of information gained per received symbol. So in other words, it is the measure of the amount of information that can be obtained about one random variable, say x, by observing another random variable y, okay? So we know this random variable s contains the information we need. So when we observe y, then we should be able to decode x, okay? So the act of observing y with the in hope of decoding x is the mutual information. So it is important in communication where it can be used to maximize the amount of information shared between what is sent and received, okay? Because with this, we're able to tell the capacity of the channel. And then statistically, the mutual information is described as sigma xy, the joint probability distribution times the information times the mutual information. Okay? So you observe that the I of xy is weighted by the joint probability distribution over the possible joint event. And here, this information, the joint information, is the same as the log of P of x given y over P of x bits. Okay? So it is also the same as log P of y given x over P of y bits. So if this is true, then the mutual information can be represented as sigma xy, P of xy, log to this 2, P of x given y over P of x bits per symbol. Okay, and now soon from this, we should be able to relate the mutual information with the relative entropy. Because now we're trying to observe two parameters, you know, one relative to the other. So in terms of the relative entropy, let's see what we get. So let us recall Bayes' theorem, okay? Let's see if we'll be able to evoke Bayes' theorem here to play with one or two things, okay? So if we recall Bayes' theorem, so you see that the joint probability is the same as the conditional probability times the other probability. Okay? And if that is true, then it means that this is the same as P of xy divided by P of y, right? So if we substitute this value into this value, then it means that the mutual information will be the same as sigma xy, P of xy log P of xy over P of x times P of y. P of X, P of Y. Okay. And now, you will recall that the relative entropy, let us put that in a different color, from what we just saw between PQ is the same as sigma P of X log P of X over Q of X, right? Now, if that's a relative entropy, you observe that P is equivalent to the joint probability distribution here, and the product probabilities is the same as the Q distribution here. So, and as such, we can now say that the mutual information is the same as the relative entropy between the joint distribution and the product distribution. Isn't it? And this, being the expected value, is the same as the expected value between X and Y log P of X, Y divided by P of X, then P of Y. So this is the mutual information. So you observe that the mutual information is the same as the relative entropy between the joint distribution and the product distribution. So hence, mutual information is the amount, is a measure of the amount of information that one random variable contains about another random variable. So in other words, we can now put it more formally that it is the reduction in the uncertainty of one random variable due to the knowledge of another random variable. Okay? And from this, we can easily play with some of the properties, okay? Can easily play with some of the properties of mutual information, and I believe you should be able to prove those ones, right? And we have quite a number of them in the video. So I don't know if you still want us to walk through them. Do we still need to do that? Going by the proof we've had is the same, it follows the same discipline, or you want us to still look at them? Hello? Are you with me?
We can get the one from the videos.
You can what?
Can work with the one on the videos already. The YouTube.
Okay. Okay, fine. So that sounds good. So so we can now move on, because here we see that from the properties, the mutual information here asymmetric. Then also there is a relationship with the chain rule, such that h of X, I think we have all the proof in the video, so given Y, and then the same as h of Y minus h of Y given X. And then we also have that the mutual information is non-negative, because we're also able to show that the relative entropy between P and Q is non-negative, and as such, the same rule applies since they have similar relationship. And then there's a self-information, okay? The self-information. So the amount of information observed about Y from about X, for instance, from X, or about Y from Y, so that the mutual information between X and X, between the input symbols, is the same as the entropy. So we equally have the proof, so where you use the log sum inequality and the law of total probability to, you know, prove that. They're just few lines. And then we have data processing, okay? So data processing. So we also have this in the video. I'll just mention it because it bears with Markovity. So, so data processing actually is used to show the manipulation of data, okay? So with this, we are able to consider, for instance, the information we can gain from a process whereby we relate XYZ by a Markov chain or a Markov distribution. And you see that, fine, we can actually gain so much information about X from Y. But for us to get information about Z, about X from Z, then we have to learn about Y, okay? So, well, we can actually gain information about Y from Z without any formal conditions. But there are conditions to gaining information about X from Z. Because by the Markov chain, they are not directly linked, okay? So here we now say that if X, Y, and Z forms a Markov chain of this form, then if the joint probability mass distribution, say for this is P of Y given X, while this is P of Z given Y, can be written in this form. Then we now see that the probability of X, Y, Z is the same as probability of X times, where this is the probability of X, times the probability of Y given X, times the probability of Z given Y. So here, the implication is that the Markov chain exists if and only if. So this Markov chain exists if and only if X and Z are conditionally independent, given by P of X, Z given Y is the same as P of X, Y, Z over P of Y given P of X, Y, P of Z given Y over P of Y, which is the same as P of X given Y, P of Z given Y. Well, all of this is explained in the videos and all of that. And should Z now be a function, then no processing of Y, deterministic or random, can increase information Y contains about X, okay? So intuitively, we now see that the mutual information between X, Y is greater or equal to the mutual information between X, Z. So it means that the mutual information between X and Y that are connected by this Markov chain is definitely greater than the mutual information between X and Z, because they don't have the direct connection, okay? So put differently, the mutual information between X and Z is less than or equal to the mutual information between X and Y. So this now brings us to a light communication system where we now have to go through different networks. Let's assume I need to route a call from my mobile network to a landline, okay? So it means that at some point, we need to leave the mobile network operator to the telephony network. There are two different networks altogether. So it means that the information I will have to gain about that network is strictly dependent on the information my network has of that network. Okay? So I have less power over that network. But should we now talk about my own network relative to my device, then there's no problem because we have a direct link. That's what we're just trying to talk about. And this helps inform the data processing inequality And there we now make mention of some interesting mathematical assumptions, the sufficient statistics. So you want to look up the videos and the Fanos inequality, because those, we are going to evoke them when we begin to talk about relative entropy, okay? Especially the Fanos inequality and the like. So we have all of those things, you know, all put up in in the videos. Well, we said we're going to end our class by 5, and this is just a minute to 5. So I don't think I want to push us any further, but though I have some other topics I would have loved to, you know, treat today, but we'll push them to a later time. So any question, please? Is there any question?
So there is no question at my own end, but there is a request I want to make. So,
okay, go ahead, please.
I want to ask if it's possible for us to have past questions so we can be working with it and prepare better for exams.
Okay, I think one of those guys in this class should have my past question.
Okay.
Yes, so he should be able to supply that. Alternatively, I could share it. That's not a problem.
Please, sir, you can do that to help everyone.
Okay. So
Thank you, sir.
That won't be a problem.
All right, sir. Thank you.
Okay. So any other question, please?